end up having to rush the end because I'm too optimistic in what all I can explain. So let's try to do it better. So today we'll talk about fluids and the first part of fluids, grid-based methods or Eulerian methods for fluid simulation. The remaining part of fluids will be covered in the week after the spring break, and that's also when your fluid homework will be announced, and this whole thing will be a recitation by Harmony. She'll give you her perspective on that. So fluid simulation is a big sort of industry. The CFD, continuum fluid dynamics, that's like even a topic in computational physics. And of course, our applications, we are talking about like game, film, visual effects. That's just a small part of it, right? Because as you can imagine, fluids, when you are doing weather predictions or analyzing aerodynamics of things like cars or helmets or stuff. And even when you are doing some astronomical computations, so there's like lots of scientific computing around that. We will be looking at, of course, or our discussion will be focusing on the entertainment type applications. So one big customer is films. I guess I should point out that the good resource for fluid simulation, I don't know if I put it there. There's a great book if you want to study this in more detail. We will only cover the very basics, but there's a great book by Robert Britson. I think I have the reference in some of the later slides, just in case I forgot. Fluid simulation for computer graphics. He also has the course notes, which are freely available online, and that's a great resource. That's essentially what this lecture is based off. And I guess I'm mentioning it because he recently moved to industry, to Autodesk, to roll out his professional fluid simulator. Games, and I don't have a slide on games. Games are using it a little bit to a lesser extent. I guess you know better the modern games than I do. I know that the NVIDIA guys, they do some fluid stuff in games, the physics stuff. There's even a thing called position-based fluids. I'm not planning on covering that. That will be related to SPH. That's what will be the second lecture in fluids. But let's get to the basics.
Are you covering position-based fluids? Are you covering position-based fluids?
I wasn't planning on, but if there is enough interest, that maybe we can cover. There is some flexibility after we cover all the three homeworks. The homeworks are like the basic part, and then there's your final project, and there is some sort of customizable part. So we can put there some lectures you would be interested in. I'll be also gone a lot, so we can find somebody who knows a lot about that. I always feel a little bit bad about teaching about fluids. I know the basics, but I don't have as much experience with this with the other stuff, like the position-based dynamics. I actually coded up at Disney, and so I really got my hands dirty with it. With fluids, not so much. So it's best to learn from somebody who actually did it. That's exactly what I tried to do with the rigid bodies, right? With Robin, who actually did it. So I can, if you are interested in something like that, I think position-based fluids. I think that's exactly what Harmony will be implementing for her thesis. So maybe she could do a lecture on that if people are interested in that. Let's do the basics now. So we will go first over the difference between Eulerian and Lagrangian viewpoints. That's a very important thing in fluids. Then you already know that the fluid behavior is governed by Navier-Stokes equations, which is a very important example of partial differential equation, PDEs. That's what we discussed the last time, right? And we'll show you how you can derive the Navier-Stokes equations from basic principles, the basic principles being Newton's second law of motion and some other standard things. And as you know, the continuum math is just one side of the coin. The other side of the coin, equally important, is the numerical solution. As you have already seen the last time, right? Just having the PD doesn't really mean that you can solve it. To solve it in a discrete world, we need to invoke some tricks, and that's the numerical solution part. Okay, so the difference between Eulerian and Lagrangian viewpoint, that's actually very important. So in Lagrangian viewpoint, we are tracking individual particles. You can think about the particles as small blobs of fluid, or even individual molecules of fluid. If you want to think about it that way, why not? And each of the particles has some properties. it has some position, some velocity, it can have pressure associated with temperature and whatever. Some parameters are associated with each particle. And as the fluid moves, right, that's the whole point. We want to be simulating the motion of it, animation. As the fluid moves, then the particles move around, and also their parameters change in time, right? Like the particles can be cooling if the fluid is changing its temperature. Now, on the other hand here, the Eulerian viewpoint means that the observer is not sitting on a particle. So on a Lagrangian viewpoint, the observer is sitting on the particle and measuring the properties of the fluid at a particle, like the temperature or pressure or velocity, whatever. In the Eulerian viewpoint, the observer is fixed. So we have a grid. That's why we call it grid-based method sometimes. So we have a grid, and at each of the grid points, we have an observer who is making some measurements. So in Eulerian viewpoint, we are measuring the velocity, pressure, and so on of a fluid at fixed locations in space. For example, the grid points here, okay, or the centers of the cell, right? That's just the detail. But the point is, the location of the observer, the location where we are making the measurements does not change. That's fixed, okay, in the Euler viewpoint. And these viewpoints are fundamentally different, right, as you can imagine. We already noticed that when we did the 1D advection example the last time, because here we need to, if I'm here and I'm measuring some quantity of the fluid here, it's not just the effect that, for example, if it's temperature, there's not just the effect that the fluid would be changing its temperature, but it's also moving around, right? If you remember what I was saying on Monday, if we have the temperature profile on a 1D country and there is a wind blowing it from left to right, then if you are at a fixed location in space, the temperature can be changing even if every single molecule is keeping its temperature. And that's just because the hot air is being replaced by cool air, for example, or the other way around, right? So that's why in Eulerian viewpoint, the changes or derivatives of the quantities are a little bit different than in the Lagrangian viewpoint. The difference is really just the advection. So
what exactly are you measuring in the grid? Like, is it number of particles or your some sort of average temperature?
So the most important quantity is the fluid velocity at every grid point. The other thing we will need is a pressure. I will explain that in a second. But the key thing is the velocity, essentially. And then if you are doing, you will be doing smoke sim for your homework, so then you will have also think like smoke density. You can have the temperature if you care about that, right? Those are like the special things. Okay.
Is that the analogy for?
Let me put in this one. Does it work still? Yeah.
You had some analogy for Lagrange in the last one.
You mean this thing?
Read it.
Oh, that's sort of what I tried to explain already. So this, if you want to anthropomorphize it, then here the observer is like floating in a balloon, which is being carried away around with the fluid. Like imagine doing a weather forecast where you are in a balloon and the balloon drifts as the air blows it with it. And you are making the measurements there, right? As opposed to here, you are really stuck on some point in the ground or like somewhere high up on like some tower, meteorological tower. Just trying to make it more dramatic, I guess. But this is the key idea. I think you got it, right? So we'll go over the Eulerian viewpoint today. The Lagrangian and Eulerian, they have quite complementary properties. Like what is easy in Eulerian methods is hard in Lagrangian methods, like achieving incompressibility. That's one thing we will require from our fluids for good reasons. So both of these techniques are studied quite a bit in computer graphics. These are typically called the grid-based methods, and the Lagrangian models, that would be the SPH or position-based fluids, where you really have these little particles. So people investigate both of these approaches because they have really complementary uses. So it's not like you can pick a clear winner, depending on your application, right? For some application, one of the viewpoints might be strictly better. but you can't really say this one is the best in all cases.
What about performance?
That's a great point, yes. And again, sort of depends, like what sort of resolution are you looking for, right? Like here you will need to have a bunch of particles. Here you will need to have small resolution of the grid, right? Like, and what sort of effect do you want to achieve? If you want to create some splash when the fluid will like go far away, right? Then a grid would probably be a bad idea because the grid is like focusing on some region in space. But then I'm sure that people have like answers to it, right? That you can do like adaptive grid and you can replace it with a mesh and so on. So. Okay, so we will go over the Navier-Stokes equations first. So quick reminder of the notation. I guess you have already seen it a bunch of times, but it's good to, even for me, to remind ourselves what do we mean by this. So first of all, here the U is, so this goes from some domain, let's call the domain omega. That's the domain where we are simulating the fluid. And here the U, this U is a scalar function. So the gradient of a scalar function, this gradient U will be a vector function, omega to R3 if you are in R3. By the way, it's entirely reasonable to be doing fluid simulation also in 2D. Or 1D, but I guess that's less interesting. Here this U is a 3D function. So that means that goes from omega to R3. So this is like the boldface, this is like a italics for scalar, for vector. So this is divergence. That's what we discussed the last time. And this ux, uy, uz, that denotes partial derivatives. Partial of u by x, partial of u by y, partial of u by z. Omega, that's the domain where I'm simulating more fluid. So omega, if I'm in R3, omega would be a subset of R3. So if we are talking about the grid-based method, it would typically be some box of fluid. Just saying that this function is defined somewhere, okay? And we will be using U for the velocity field of the fluid. So imagine you have a box of fluid, typically discretized using some box. No, Navier-Stokes is continuous, so you don't have to discretize it there, but you can think about the discretization too. And every point we are measuring the velocity of the fluid at every point in time. So that's what this U will be denoting, okay? And the Laplace operator, we had it the last time. The Laplace operator is the divergence of the gradient, and that's either denoted like this or like this. In both cases, it means Laplacian. And on the Euclidean domain, it's just the sum of second partial derivatives. Okay. So in fluids, in Navier-Stokes equations, we'll actually put all these things together. It's quite cool. I guess here is a reminder of the advection. Or simple PDEs like we discussed the last time. This was the advection equation, so this was the temperature profile being advected or carried away with some wind with speed c to the right. In 1D the gradient is a little bit funny because in 1D the gradient would be just derivative, but in general we are looking in 2D things, so that's why we put the gradient there. And diffusion, this was the heat diffusion equation, right? Heat diffusion is sort of nice to put it together. The advection advects it, moves it to the right, and the diffusion, what the diffusion does, it's sort of like, imagine this is temperature, and then it sort of equalizes itself. That's what this PD would be describing. And this is just sort of like an offside, just to discuss the notation a little bit, practice the notation a little bit. Now, what's very important are the Navier-Stokes equations. So let's discuss that on a few slides now. So first of all, there are two parts to it. There's the first part, conservation of momentum, which you can derive, and I will derive it in a second from the second Newton's law of motion. And there is conservation of mass, the divergence-free, the incompressibility condition. So I guess first, this at first I guess it looks daunting unless you have already seen it before. So we will go through it one step at a time. to sort of break it down and understand what the Navier-Stokes actually means. Because it looks complicated, but there's actually nothing that special going on there. So the U, as I said, that's the velocity, and it's the vector function defined on some domain, typically on a box. If that's where we are simulating. That's the easiest thing we can be simulating. Now P is a scalar function of pressure. We'll explain the pressure. I guess, well, you know what pressure is, right? Pressure is force per area, right, intuitively. And in the fluid, the gradient of pressure essentially tells us where the fluid wants to go. I have a slide on that later. Density, you know what density is, right? It's mass over volume. That's how dense the fluid is. So water has about 1,000 times denser than air. We will be talking here just about simulating single type of fluid. You can do also like interactions of fluid, like I guess in nature almost always water surface would be interacting with air, but for us the air is so negligible that we can just ignore it as if the air was not really there. I mean, there are papers that do like air bubbles, but that's advanced stuff. We'll go over the basics. G is the gravity force. That's our old friend. And this mu, I think that's, no, is that mu? What is it? I need somebody Greek here. I know. Well, that's the mu. New? I think something. Anyway, it's a viscosity, kinematic viscosity, which basically tells us how it's something like the damping coefficient we had before, and that's something that will be high for like thick viscous fluids like molasses, like honey, and will be low for like water or even air. Okay, so let's break down the first part of Navier-Stokes, the momentum equation. So the first, this first thing is called advection, and that essentially has to do with the way that we are doing Eulerian measurements here. Okay. This is the pressure term that basically tells us where a blob of fluid wants to go due to pressure of adjacent blobs of fluid. This would be some slowdown. This is sort of like damping due to viscosity. So I guess what we can look at we can look at it as if we have a small blob of fluid at some position, which has some mass, volume, and velocity. And I would like to show you how to derive the Navier-Stokes equation from Newton's second law. So F equals ma. Okay. So what we actually start with, like a funny. We will write the acceleration in this funny way, the du over dt. This capital D means this is what's called material derivative, and essentially means that we are for a moment taking on the Lagrangian viewpoint. So we are looking at the velocity of the particle in this case, measured from an observer sitting on the particle. Okay. The whole point of this is to abstract away the advection for a second. The only difference between the material derivative and this term here is the Eulerian thing, the advection. Okay, I will explain it in more detail. Okay, so let's look at it this way. We have a blob of fluid, and we want to figure out how that blob will be moving, okay, and how its quantities will be changing, how its velocity will be changing, and if it has some other quantities like temperature. So we could also, well, here we only care really about the velocity. So how its velocity will be changing, okay? So its velocity will be changing because there will be some forces acting on it, okay? So the first force, well, the easy force is the gravity, right? It's just a constant force. That's never a problem. The other very important force is the pressure force, the force induced by the fact that this blob is not there by itself, but there is some fluid surrounding it, and the force acting on this blob of fluid will be equivalent to the minus gradient of pressure times the volume. I guess the intuitive explanation is that you have some distribution of pressure in your liquid, and what the blob of fluid wants to go, it wants to go from high pressure region to low pressure region, right? If you look at the pressure as a scalar field, then the gradient will tell you the direction where the pressure increases the most. If you go minus gradient, and when it decreases the most, that's exactly where it wants to go, right? Like imagine high pressure, low pressure, it wants to be sucked in there. So that generates a force on our blob of fluid. The other type of force is viscosity, and that's similar to what we had as damping in mass spring systems in elastic solids. Viscosity essentially means that diffusion of velocities, that if a blob of fluid is moving too fast respectively to its surrounding blobs of fluid, then the others will sort of slow it down, so like internal friction type of thing. And this is exactly captured by Laplacian, and the viscosity coefficient is this new thing that tells us how strong that effect is. It turns out that actually we typically don't need the viscosity, just like well, that's not true that we don't need damping so often, but there will be some artificial numerical viscosity, so this term is actually less critical than the remaining ones, because even if you don't put it there, it will still work quite well. Okay, so if we put it all together, so this is the Newton's second law written with the material derivative. I'm still owing you the advection, but I will do that in a moment. So now we will replace the forces with what we discussed. Okay, so first the gravity force, mg. The other force is the pressure force, so that's essentially the integral of the gradient of pressure. So if we replace the integral just by multiplying by the volume v, we get this contribution. And this would be the viscosity. So the viscosity is captured by the Laplacian view. So you can look at it as curvature. Like if there is some high curvature region of the fluid, then the resistance due to viscosity will be higher. Whereas if like the entire mass of fluid is moving, for example, with constant velocity, then there will be no viscosity because the particles are sort of not like sliding over each other. Just trying to give you an intuition. So what we do now, we divide by the volume. Okay. So if we do m over v, we get the density, we get rho. So here the v disappears. Here v also disappears. Here we get rho. So that's how we get this. And now we can divide by the density. Okay, and we get this form. And that's almost already the first part of Navier-Stokes equation. The only thing we need, we rearrange it to, well, it's already rearranged. We only need to expand this mysterious material derivative term. Okay. So remember the material derivative was looking at the changes of velocity from an observer that was attached to the particle, to the blob of fluid we are studying. Okay. So if we want to convert it to Eulerian measurements, we need to take the advection into account, right? Just as I was saying before, if the observer is actually at a fixed point in space, it needs to take into account the flow of the fluid that moves it around. It gets a little bit tricky because here it's applied to the velocity itself. Okay, so we are looking at the changes of velocity also due to the velocity of the fluid itself, right? It's a little bit confusing, but it's actually nothing that special. It's easier to understand it when you're looking at a temperature profile, because that's not the advection applied to itself, if I'm making sense. But if you think about it, it sort of makes sense, right? Imagine you have a box of fluid, and if the box of fluid at every point I'm measuring the velocity of the fluid, right? If I let the fluid move, the fluid moves according to its velocity, right? And the velocity also changes as it's being carried away, right? Imagine some flows with some velocity, so as it propagates, the velocity needs to be advected as well. So mathematically, it's actually probably easier to think about it, because all you need to do to account correctly for the advection is to use the chain rule. Okay, so if we have some quantity q, the q can be absolutely anything. the most important case is when it's the velocity, but it could also be the smoke density. It can be color if you will have a colored fluid like for your project, or temperature. We can be advecting any quantity. Okay. Again, imagine a vector field. Every point has a velocity, and there is some other function q in the vector field, which is being advected around by the velocity field. Okay. Well, the way we do it, the quantity depends on time and the spatial position x. Okay. But the trick here is that the spatial position x, we are sort of, if we are taking the, maybe I should put there this one, the capital D over dt to be consistent. This is the material derivative. Okay. So here we are looking at a blob of fluid which is itself moving. Okay. So here the position x is not constant but depends on t. Okay. So if I want to differentiate this properly, I need to use the chain rule. So the first variable that just differentiates directly, but for the second one I have to take into account the changes of x with respect to t, because I am on a blob of fluid that's moving itself, and how it's moving, well, it's moving as a dx over dt, which is exactly my velocity. Okay. So here, what we have here, this is just a scale. If q was a scalar function, then this is also a scalar. And here we have a dot product. This is the gradient of q. So how locally is it changing? And this is the velocity at that point, at that Eulerian measurement, at the Eulerian point when we are making the measurements. Okay. Again, it's exactly the same idea as I was saying before. If you wanna understand this, then walk in your mind, visualize this example of like the temperature profile of air being advected around. This is my temperature profile. If the whole thing moves to the right, and I'm an observer sitting here, then what I will be measuring here will be exactly this, if this moves with some velocity. Okay. Yeah, if it's not clear, then try to go over this by yourselves. It's also very nicely explained in Britson's book. This probably takes a little bit of getting used to. But ultimately the formula is very simple, right? Ultimately the formula is this, and that's exactly the advection. The advection term here. So that's this term here. So if you are looking at this as material derivative, so wait a second. Yeah, that's the expression from the previous slide. So here we apply it to the velocity field itself. Here we say that the q is the velocity field, and we get this here. Okay. I guess I sort of prefer it without the brackets. I guess it's just a notational thing, but you can also look at it like this, right? So don't be confused by the fact that the velocity has three components, x, y, z, because you can be just advecting each of them independently. Okay. Here we are advecting just a scalar quantity, and u is a vector quantity, but it doesn't matter because all you need to do is advect the x, y, and z components separately. Yeah, if you were studying it in the Lagrangian viewpoint, if you were looking at the velocity of a particle, or the particle itself is moving, then you don't need this term. This is really just the term that compensates for the fact that if you are a fixed observer, the fluid moves around you, and this is exactly the term that accounts for the motion of the fluid. Okay?
And that is the advection?
Yes. This part is the advection. I guess we will call advection the step to actually implement this in an integrator. Actually, maybe that will make it even clearer. So, the viscosity is something. The viscosity of water is small, so we typically ignore it. As I said, we typically have the opposite problem. Just like you have seen in implicit Euler time integration, we have some artificial numerical damping, which sort of manifests as in fluids as artificial viscosity. So if you just throw that away, that's okay. Now it's actually quite different in SPH or in particle simulations in general, where you need the viscosity to stabilize the system. But that will be the discussion for the next lecture. Okay. Now, so this is the first part of Navier-Stokes. That's the momentum equation. And now, what about the divergence-free condition? That's derived from incompressibility. Okay, that's the easy part. You already covered the hard part of the Navier-Stokes equation, and the easy part follows from incompressibility. So I need to explain this a little bit, because you could immediately point out that water actually is compressible, right? And that's why sound waves can travel in water, right? That's how like sea animals, like whales, can communicate, right? So that's actually a very important thing, except that it's not really important for us, right? For animation purposes. Like certainly if you are doing some physics and you want to simulate how waves propagate in water, then you need to take this into account. But for our type of simulations, for some visual effects, like some splashes, this is absolutely irrelevant, essentially. Once you get to this scale, they would have to be like looking at it with a microscope or something to even notice something. So what we do, and this is by the way, what we do, we assume incompressibility as a mathematical idealization of our fluid, which is justified by the fact that it just looks good. It's a similar type of assumption as we do in rigid bodies, right? Rigid bodies also don't exist. Nevertheless, it's very convenient to assume in our simulation that we do have rigid bodies. So they're like model. We consciously accept some inaccuracy of our model. Okay. So here it's incompressibility. So what incompressibility means, and that's what this is the second part. It's sort of like the constraint. That's the constraint on the velocity field, and that expresses this. It's called divergence-free condition. It expresses the very intuitive notion of what amount of fluid enters a cell has to also exit. Okay. So I don't have any source or sink at any point on my simulation domain. I could have that, of course, if I specifically ask for that. If I actually want to create some source or sink, like if I want to generate some fluid, like if you have some like valve or something. But by default, the fluid should not be appearing or disappearing by itself, right? That would not be good. So if we are using the Eulerian domain, that's actually where the Eulerian domain, the grid, is super useful, is to accurately capture incompressibility, because we are looking at a small box of fluid, right here, a small square. So here it really means that if I have some velocity which is moving fluid here from the right and from top and from bottom, then the same amount must exit on the other side if incompressibility is to hold. Okay, what goes in must go out. Okay, so maintaining this divergence-free condition, that's the tricky part, and that's where the pressure also comes in. Okay. So in a sense, the pressure is essentially the Lagrange multiplier associated with incompressibility. The pressure is what helps you make your fluid simulation incompressible. Okay. When taking boundaries into account. Okay, let's look at this. Oh yeah, this is for the continuous case. Okay, so yeah, so how do we enforce incompressibility? Okay, so this is what we want to enforce. Okay, we want the divergence of U to be 0. That's what's meant by the divergence-free, right? That's exactly what this was like the discrete version of that. This is the continuous version of it. It's the same idea. This is just for infinitely small blob, okay? Or if an infinitely small cell. So what we will do, so this F is something that will be taking into account the advection and the viscosity and the gravity and these things, and it will produce some intermediate velocity field, U prime n. And what we will want to do now, we will want to take into account the pressure in such a way that we get a divergence-free velocity field at the end, okay? So what we have some intermediate velocity field u prime n. We want to integrate the, or we want to, time integrate the gradient of the pressure such that we get a divergence-free velocity field un plus 1 after we do this, okay? So this is what we have, and this is, let me put it like this. We want this. We want divergence-free condition to hold for our velocity field on our time step n plus 1, right? Like imagine we will be time stepping the fluid simulation forward, and this is sort of like going through the loop. So how are we gonna do this? Well, we will take the pressure update here, and we will take the divergence of both sides of that, okay? So we will take the maybe let me try to write this, let's see if it will work out. Un plus 1 equals the divergence of u prime n minus delta t 1 over rho, the divergence of the gradient of pressure, okay? This I want to be 0, okay? And this is exactly what I have here, okay?
Do you mean to have two divergent symbols up in the formula you wrote?
You mean here?
Oh, yeah. Right. Okay, so you're doing the bottom one,
No, I think it's correct. I put the divergence symbol here. Yeah, this is a silly notation because this is just the delta t. This is not a Laplacian of t. This is the delta t is the time step. Okay, this really means just forward Euler on the gradient of pressure. So this is the force due to pressure integrated forward by step delta t. Yeah, sorry about the notation. Maybe I should change it to some h or something, right? So this is how we get this. Everybody cool with that? And now this is just flipping it on the other side, and this is what I know. Okay, so the right hand side, the whole right hand side, I can compute the divergence of it. That's what I also know, right? And this is the divergence of the gradient. That's a Laplacian. Okay, notice that Laplacian is a linear operator. So after we discretize it, this will give us what? I will go through the discretization slowly, but you can already see where we are going here. Exactly. Yes. So this is what we, by the way, this is what we discussed the last time we talked about PDEs. This is a Poisson equation. Here, this is a Laplacian divergence of the gradient, and there is some right hand side. Okay, I guess I could say that's why we discussed this particle or PDE the last time, because it appears in this pressure projection step. Okay, so let's go over this again in the context of numerical discretization. So if something in the continuous math wasn't making sense, here you have another opportunity to sort of catch up in the discrete world, and that's the one that actually matters at the end of the day when you are implementing things, right? So as I mentioned, we have this unfortunate notation that the time step is delta t, but come on, you should be used to delta t, right? That's a time step. So that's the discretization of time, and we need to discretize the space as well. And in fluids, there is one very cool trick to discretize the space. Remember how I was sort of bitching the last time about finite differences, that there is no great finite difference scheme. You can do forward, backward, which are biased. You can do central differences, which have the null space problem. Remember, that's what I was saying on Monday. Well, there is a cool way around it in fluids, and that's called the MAC grid. MAC, why is it MAC? I think it's from some people who invented this.
It's Marker and Cell.
Oh, Marker, yeah, Marker and Cell. Yeah, right. So the idea is you have a grid, okay, but the cool idea of the grid is that what we need to store on the grid are velocities. Okay, so if I'm doing a 2D fluid simulation, that's what I'll be illustrating it on, then I have two components of the velocity, the u component and the v component, okay? And the velocities I will represent on the midpoints of the edges of the grid. That's I will be measuring the velocities in my discrete representation, okay? And the pressure I will put right in the middle of each cell. Okay? And why do you think this is a good idea? This is like a staggered grid, if you want to think about it this way, right? Like pressures are in the middle of the cells and the velocity values. So here we have the u components of the velocities, and here we would have the v components of the velocities. I hope it's obvious to see how we would generalize it to 3D, right? If you have a 3D grid that you just one more velocity, the pressures would still be the same. Well, why this is such a great idea, and this is used almost always when you are doing, okay, I should not be making these bold statements, I don't know the literature so well, but it's very useful in fluids, and here is why. So what was the problem with finite differences? The problem with central differences. The problem with central, let me just recap what I said before. The problem with central differences, if you have just in 1D, so if this was my xt minus h, this was my xt, this was my xt plus h, and if I said that we are doing central differences to approximate the derivative at t as xt plus h minus xt minus h divided by 2h, that's the central difference approximation of the first derivative at this point, right? What is annoying about it, that's ignoring the value here, right? And I showed you this example. If I happen to have a function which oscillates like this between +1 and -1, then the central differences will just tell you 0, okay? Which is very far from what you probably should be getting, right? That's called the null space problem, that these crazy oscillatory functions are in the null space of this operator. So the cool thing about the mag grid is that by the staggering, it essentially gets away from this problem. I guess I can explain it here. The trick is sort of like a little bit out of the box thinking, that you will not be evaluating the derivative here. If you evaluate it here and here, they're perfectly fine, right? Because you don't have samples there. Your samples only live here, here, and here. So in the middle of the interval, where you don't have any actual values, you can safely use central differences. This problem will not occur because you don't have a value there. Okay? What you have to pay, what you are losing, is that now you have to be dealing with these staggered grids, right? In the case of the mag grid, that's my mag grid. In the case of the mag grid, we have the velocities here and the pressures somewhere else. Okay, so that has some disadvantages because sometimes we will need to interpolate, right? For example, oh, actually, I have slides on that, so I'm getting ahead of myself. Yeah. So let's see.
Can you explain that part? The part that you were drawing.
You mean the null space thing? Yeah, so okay, great. That's exactly what's on this slide, actually. So that's basically what I was drawing. So the null space problem is that so you would expect that only constant function will give you 0 derivative, right? That's what it should be, right? But the problem is that if you do central differences, the way I said before, if you just evaluate the central difference here just by looking at these two guys, then you have these oscillatory functions which also look like they are constant, but they are not, right? There are some ways how to get around it. You can use forward or backward differences, but then you have the problem of being biased either to the left or to the right, right? And that's why we had this upwinding scheme, which sort of decides which way you actually should be biasing. So in some cases, that's the right thing to do. But in fluids, I think the right thing to do is to use the staggered grid. So that's what the mag grid really is. Because now, if I have value here and here, getting a central difference approximation for the first derivative here is obvious, right? And the null space problem isn't there because you just don't have a data point here. Okay. There is, of course, a flip side of the coin. The flip side being that you sometimes have to resort to interpolation, right? For example, if I want to know what is my u component of the velocity here, then what I have to do, I have the velocity here and here, right? Here would be my u I plus 1/2. Oh yeah, notice that this is u I, so I and j, that will be the index of this, and this is u I plus 1/2 j. Okay, so I moved half of my cell. Okay, so this would be u I plus 1 j plus 1, right? So if I want the value here, I just have to average this value and this value. I have to interpolate. So that's a slight downside to it. But I think that the advantages outweigh this slight disadvantage. Okay, is that clear?
Why would you need to interpolate it? Why not the cell below it allow us to calculate that?
Yeah, why do we need to interpolate? Yeah, we will get there. We will need to do that to do the advection. That's where we will need to interpolate. The funny thing is that you would need to interpolate probably even if you were not using the staggered grid. So I don't think that's actually like a real deal, a real problem. Again, I have someone who has more experience could be could be proving me wrong. Okay, so now we have the discretization. Now we have the Navier-Stokes equation. Now we have to figure out how to actually solve the discrete PDEs. Okay, how to do an actual numerical procedure which can compute how your fluid will evolve in one time step. Okay, so basically time integration of this partial differential equation of the discrete Navier-Stokes equation. Okay. And the way we do it, or the way people figure out how it's best done for our graphics applications, is the trick called operator splitting. It's a super simple idea. Basically, we have multiple components here. I guess in general, you can look at it if I have even ODE in this case, and I have several contributions to the right-hand side. I can just integrate them one at a time. Okay. So I can first integrate the F1. Get some intermediate value Q prime, and then integrate F2 on top of that, getting the final result. So we will use exactly this strategy when we will like add one of the components at a time. I guess it's sort of obvious approach, and it works well. Okay, and we will do this. The order now will actually matter. So we will split the integration of the discrete Navier-Stokes equation into several parts, several pieces. For each of the pieces, you can write a piece of code. The important thing is each of the functions will have some assumptions on the inputs and will guarantee you something on the outputs. Okay, like for example, the pressure projection, the final step, will guarantee that you will get the divergence-free velocity field, and similarly the advection block will require that you are giving a divergence-free velocity field to begin with. Okay, so the order is actually important here, as you can get some funny artifacts. So the actual blocks we will need, the first one is the advection one. Actually, it's like that's where the interpolation will come in play. Then we'll be adding the external forces. That's the easy part, and then we will do a pressure projection. So let's go over all these steps. So the advection block. The advection is solving this PDE. Actually, it's probably a good idea if you are writing a simulator to write advection in a generic form, not specific for the velocity, but generic for any function q. Okay, because maybe you will not be advecting just the velocity. Maybe you will be advecting also like smoke density or temperature or color or whatever you want. And the same numerical routine can be advecting whatever, of course. What exactly is being advected, that's irrelevant here. So here is a PDE for advection. And the first thing you would think about would be to replace the derivative with finite differences, right? And you've got a forward Euler scheme for advection. You could do that. That's totally cool, except that it doesn't work. Here, it's exploding all the time. It's sort of interesting. I never tried this. You can try if you want. But it's supposed to be unstable regardless of how small delta t you have. Eventually, it will always blow up. So that's not a great integration technique. So that's why people, specifically Jostam, developed a different advection algorithm called Semi-Lagrangian advection, which is a sort of cool idea. It was 1999, Jostam's stable fluids paper, very cool paper, which I think sort of made these efficient graphic C fluid simulations possible. So what is the idea of semi-Lagrangian method? So we are talking, all this lecture we are talking about Eulerian methods, okay? The observer is sitting at a fixed point in space. The idea of a semi-Lagrangian advection is to, for a moment, look at the particles and trace them. For a moment, assume that we actually have particles there and use that as a concept to figure out the advection, okay? So let me explain that. So, So we are doing Eulerian measurements at some point in space here, okay? And the point currently has some value q, okay? And what the advection is essentially trying to figure out is what value will there be after we make one time step, okay? So if you think about it as particles floating around, we can figure out what value will go there by tracing the velocity field backwards, okay? Because if you have a time step delta t, all we need to find out is which particle will arrive to my point in the time delta t, right? And then if I have a velocity of this particle, that's what I will just copy there. That's really the idea of advection, right? So like for a second, you sort of assume that these are particles, and you essentially trace them back, and then you copy the value. Okay. So how exactly do we do that? Well, we are still on a grid, right? We don't have any particles here. All our values just live at the grid points. So that's where the interpolation will become important. So what we are gonna do, let's see what the symbols are. So we want to figure out what is some I don't know if it's velocity or pressure or temperature, and we can be advetting anything, that doesn't matter. We look what is the value of velocity here, and we basically take a step backwards with our time step delta t in the direction of the velocity, okay? We take a look at the value that's there. That's where we'll need to use interpolation. I think that's what's explained here. So we take the step back, and here we interpolate the values from the grid to the point. So we copy it there. That will be the result of the Semi-Lagrangian advection. Okay. Now here it's written that we just take one step back, but you can probably see that that's not the smartest idea, because the trajectory probably will not be linear, right? By the way, if we are doing bilinear or bilinear intuitive, you know all bilinear, trilinear interpolation, I hope. Already this is not a linear operation, right? Bilinear or trilinear, you know that. So the path of the particle will never be a straight line. So it's actually recommended to do multiple steps there. Trace it back just by a little bit, or even a smarter thing is to use like RK2, Rongekuta 2, which essentially means that you trace it back by half time step, get the velocity there to trace it back full time step. If you want the more details, then this is discussed in great detail in the book. And the Semi-Lagrangian advection has some great properties. It's like the opposite of forward Euler. It's unconditionally stable. So that's sort of cool. Regardless of how large time step you take, it will never explode. Okay. It doesn't mean it will be very accurate. The inaccuracy, I think, will manifest as the fluid sort of slowing down, so as sort of like artificial viscosity. I hope I'm saying the right thing, but I think it makes sense. Oh yeah, that's what's said here. So if you are taking too large time steps, you will introduce some numerical dissipation. So the reason why it's stable is sort of obvious, right? You are just interpolating the values you are advecting from somewhere else in the grid. And by interpolating from the grid values, you cannot really overshoot, right? So, but the error, the interpolation is essentially a smoothing filter, right? So if you are repeating the advection over and over, so you are smoothing and smoothing things, so ultimately you will smooth them to nothing, right? To just some constant value. That's the idea, which I think is fairly intuitive. Yeah, it turns out that in 1D it's equal, the Semi-Lagrangian advection is equal to the finite difference in upwinding. So remember, that's what we discussed. How do you discretize the 1D advection equation, the temperature profile being advected? We discussed it at great detail the last time, and I was arguing that you need to go upwind. You need to use forward or backward differences depending on which direction is the thing moving, right? So here you again go like against the flow to advect the correct value onto your point.
So the thing that we bring back to our point, that interpolation is figuring out what would be, I guess, velocity at a particular point at another set.
Because we only know the values at the grid points, right? So we need to interpolate, because of course when we trace the velocity, it can bring us anywhere. We'll be very lucky if we just ended up on a grid point, right? So that's why we need to interpolate, yes. And that's also, I think, how people fix this numerical dissipation effect, that you use better interpolation, right? It's like something better than bilinear interpolation. Okay. So that's the Semi-Lagrangian advection. Oh, so the second step, that's adding the external forces, that's really simple. That basically means you have seen it already in PPD, right? This is the velocity. You just integrate there forward Euler the gravity acceleration. Super simple. The catch is if you are like the advanced things which are being discussed a lot in film, where you actually want to control your fluids to do what you want. Like the funny example is that imagine you are working in a visual effects company, and a director comes and says, oh, the waves look great, but I would like the sea to look more angry. So you need to do something to control the behavior of the fluid, right? And it's not so easy to sort of just go in and hack it arbitrarily, because ultimately you still need to be satisfying the Navier-Stokes equations, or it can be doing whatever, right? So one of the tricks that people often do, that you can introduce some special type of forces that do what you want to do, right? Or if you want to create some like visual effect, like create like a character from a fluid, like a human of fluid, which then you will maybe like spill on the floor. You can also achieve it by inventing some special forces which you can integrate in this step. That's sort of like an aside. And the most critical step, I guess they are all sort of critical, but or maybe the most computationally expensive step is the pressure projection and guaranteeing that your velocity field will stay divergence-free. Okay. So advection and forces, they can destroy that property. They will not give you a divergence-free velocity field. So what you need to do in this last step is to solve for pressure while taking into account boundary conditions, such that after you apply the pressure in the pressure update, you get a divergence-free velocity field. Divergence-free meaning this, un plus 1, the divergence of that will be 0. Okay, and once you have done this, then you have finished the loop, and you can go again onto another advection and do another time step forward, essentially. So let's take a look. How do we do this? That's the last tricky part. before you can go ahead and implement it. So we need to discretize this, okay? And here is where the mag rate will be very useful, because to compute, so we need to discretize the gradient of the pressure. And remember how the mag rate, my mag rate somewhere. Remember how the mag rate looks like. Maybe I should have put it here. Maybe I'll explain it here. You know what, I'll just draw it here. So let's say I have some velocity here. So there will be some u I plus 1/2 and j. Okay. You know what? I'll do a better drawing here. Bigger. So here is my ui plus 1/2 j, so that's my velocity. And I'm trying to discretize this, okay? My pressures are here, so this would be pressure I plus 1j. Here would be pressure of the cell ij. And then the beauty of the mag rate is that the gradient of the pressure here, I can directly get by central differencing the pij and pi plus 1j, right? So that's exactly what is written here. You just, this delta x would, this is the delta x, right? That's the space. This is also the delta x. That's the grid. Oops, here is the delta x. That's the grid spacing. So this is the central difference approximation of the gradient of pressure. Okay. So this is a discrete version of this. For the u component of the velocity and for the v component of the velocity is the same thing in the other direction. Okay, so this is the pressure, the discretized pressure update. Okay, now here is where the boundary conditions will kick in. If this was a boundary and this was a solid wall, then you don't have any pressure there, right? You only compute the pressure for a fluid. If you don't have the fluid there, what the pressure means. And what the pressure means is determined by your boundary conditions. Okay, so if you have there, I don't want to go into too much detail here, but if you have there a solid wall, what you want to do is I might have a slide on that. What you want to do is you want to compute a fixous pressure on this point, on this solid cell, such that this velocity here is 0. That there is no velocity going in or out from the solid wall. Okay, so that's how you deal with the boundary conditions. There are different type of boundary conditions. If it's like air, if it's in terms like free surface of the water. Let's not worry about the boundary conditions for now. Let's finish this and then we can discuss the boundary conditions. So this is the discretization of the pressure updates of this first formula, and now we need to discretize the divergence. That's this part. Well, actually, this part first, right? So we need to compute the current divergence, which will probably not be 0. Otherwise, we would not have to be doing this. So the divergence essentially is, what is the divergence? Well, here it's, there are two ways how you can look at that. That's what confused me for a second. So you can either look at it as discretization of this, right? So you discretize the partial u, partial x, plus partial v, partial y. And again, the mag rate is making that really nice because they are, again, at the right, the ui plus 1/2, ui minus 1/2 will make it really easy for you to compute the pressure exactly in the middle of the cell, okay? Because these are just, the velocities are just waiting to be differenced, okay? So this is for the, this corresponds to the u component here. This corresponds to the v component. If you sum it together, you get a discrete approximation of the divergence. The other way you could look at it is using the divergence theorem. So over the boundary of your cell, this is my cell, and over the boundary you would integrate the velocity dot product with the normal. Okay, outward pointing normal. So if you do this, if you compute this using the divergence theorem, you will actually get the same formula, unless you do the normals wrong. The normals here, if this is my cell, the normals have to be outward pointing. So if you want, you can try this for an exercise that will give you the same thing. Sort of.
What does velocity normal mean?
Oh, this means like the velocity field, like the 3D vector field, and the dot product means the normal is also a vector. This is the divergence theorem, which says that you integrate over the boundary of your domain some vector function and you dot product it with the normal to the boundary. Okay. Okay. So after we put this all together,
on the previous slide,
yeah.
you said divergence of velocity. Is that sum of both partial derivatives? Is that by definition?
You mean this?
The first one, divergence of velocity.
Yes, that's by definition. Yeah, the divergence is the sum of the first partial derivatives. Yes, that's sort of what we started with the notation. Correct. Yeah. Okay, so if we write down the formulas, so this is what I just discussed, and here is the Laplacian, and what we talked about the last time is the discrete approximation of the Laplacian on a regular grid. That's this. Remember this is the stencil. This would be the -1 minus maybe this is minus Laplacian of 4 minus 1 minus 1. So that's exactly, if you look at it carefully, that's exactly what appears here, plus some normalization coefficients. Okay. Now, here is a quick note what to do about the boundary conditions. So I already said it quickly. So if you have a solid wall there, then you set the pressure such that the velocities you get from this update formula will be 0 in the direction normal to the wall, right? That's what a wall means, that the fluid cannot flow past it. So you compute the pressure such that the un+1 in the direction of the wall would be 0. Okay.
Is that an actual wall or just the edge of the matrix?
Well, not an internal edge, right? Like if you have a box and the box ends somewhere, then you can say this is a wall and the fluid cannot go past it, right? So the fluid can sort of like wrap around it, has to wrap around. That's what these boundary conditions will do.
So then is it the box that is subdivided into the matrix?
Well, what I mean by the box, I'm not sure I understand your question. So if I have the mag grid, this would be my grid, right? And I guess the easiest thing you can say that the rest of it is solid.
Yeah, that's what I was.
So it cannot go outside, right? So now typically maybe you don't want this. Maybe you want to be simulating some free surface, right? Some waves floating around. So that's where you use the free boundaries. And basically what that means is that you set the pressure on the air to 0. Okay. Here it's a little bit funny when you just go in between, when you can sort of interpolate between the pressure of the fluid and on the air. I'm actually not entirely sure what is the reason for this. Okay, so so what do we do? So now we have the system. Now we have, this is the divergence of the velocity field, and this is the Laplace operator. We put this into a system of linear equations. That's what we saw before in the continuous case, where the system A will be just the discrete Laplacian. Okay, that's the that's essentially the stencil -1, -1, 4, -1, -1, but unwrapped for the entire grid, right? What happens here, the pressure, like we have the grid, like here, but you collect all the pressure values and stack them into one big column vector. So the entire Laplacian, these stencils scatter into a large sparse matrix, okay? So the sparse, because there is only 5 non-zeros for each cell, the matrix will have only 5 non-zero values, at least in 2D, right? In 3D it would be 7, because you would have one up and down. So you form this Laplacian matrix, and then we need to solve it. And that's actually the bottleneck of these Eulerian fluid simulations, this pressure projection steps. So there are several ways how you can solve it. In fluids, people recommend using iterative solvers. The easiest thing you can do, you can use Gauss-Seidel or Jacobi. That works, but it doesn't converge very fast. What is a better idea is to use a conjugate gradient solver. And even better is to use preconditioned conjugate gradient. Have you heard about this? The idea to improve convergence of conjugate gradients, you use a preconditioner, which means that instead of solving the AX equals B, you will essentially be solving P inverse AX equals P inverse B, where P is some preconditioner matrix. But the idea being, if you remember CG, the speed of the number of iterations of CG depends on the condition number of the matrix A. Do you remember what's the condition number? The matrix A is symmetric and positive definite, or at least positive semi-definite, but I think once you have some boundary conditions, it's positive definite, because it's the Laplacian. And what is the condition number? Do you remember that? It's the ratio between the smallest and largest eigenvalue. Okay. The preconditioner tries to reduce this condition number, because the condition number tells us how many iterations the conjugate gradients algorithm will need until convergence. Okay. And what people found out that it works really well in fluids is to use incomplete Cholesky decomposition as the preconditioner. So Cholesky would mean this decomposition of the matrix, and the incomplete means that this L matrix has to have the same sparsity pattern as A. The problem with the Cholesky decomposition, that's what the direct solvers are using. The problem with that is that it generates fill-in, that even if the matrix A is very sparse, in our case it is very sparse, only 5 non-zeros per row or column, that's very sparse. This L might not be so sparse, okay? So the direct solvers are using all sorts of tricks to reorder the matrix A. The trick proposed here, the modified incomplete Cholesky, is to essentially force all the elements of L which are, sorry, let me rephrase that. The matrix L will only be allowed to be non-zero on the points where A is non-zero. That's the idea of the incomplete Cholesky, which turns out to work well in fluid sim. If you are, I don't remember what do we have in the, I guess we probably have exactly this in the homework framework. It wouldn't be a bad idea to try just direct solvers, because the direct solvers have gotten quite a bit better since the time these fluid books were written, so they might work also quite well, actually.
Didn't Stan use something else though?
I don't remember what did he use. It's quite possible.
He called it something called Helmholtz decomposition and just said this is a magic black box and gets rid of it.
Ah, okay. Yeah, I don't remember, sorry. you can do anything, right, to solve the linear system. Probably a great idea is to use multigrid, because you have a Poisson system, and if it's on a regular grid, then multigrid might work really well. But it's sort of tricky to get it right. Oh, here we will not worry too much about the performance. Just worry about getting it to work somehow. And the easiest somehow is to just call a sparse direct solver like in Eigen, like you were if you were implementing the implicit Euler time integration. So here is just like if you are debugging it, it's useful to use these marker particles so you can quickly visualize it. The marker particles, you just scatter them in the grid and you advect them around with the velocity. So it's a nice visualization tool that you can get nice images like this. And that's basically it. Here's the summary of the algorithm, including the marker particles. So you first call the advection routine, the semi-Lagrangian advection. Apply the external forces, gravity, or if you want some control forces, if you want the user push the fluid around, for example, you can do that. And then the pressure projection step, and then repeat. And you need to choose some time step, just like always, and render at some point, or write a frame to disk and then look at that offline.
In the second step, which goes to like which one was conservation of momentum and which one was conservation of mass? Like I remember you would
Yeah, I'm not sure. It's sort of, I think they sort of are all scattered there. Well, the conservation of mass, that's this pressure projection, right? It sort of makes sure that no fluid is being lost or created by itself. I guess you could do this. And I guess the conservation of momentum probably is the advection, actually. To think about it, it's a little bit more. Yeah. Yeah, right. The external force certainly will break the conservation. Correct. Yeah, here are the pointers. This is the Robert Britson's course notes, and there is this book, The Fluid Simulation for Computer Graphics. It's a really good book if you want to do that for real and learn that. I really recommend that. And there is just some famous stable fluids paper. Oh yeah, I have the front cover of the book here. That's the fluid sim. Okay, so right on time. Any questions which you think I might be able to answer? Okay, thank you then.